The electric field at points in the xy plane due to two point charges located at 0, 0, and 1, 0 is related to the electric potential function phi of xy given by this equation. The electric potential function will be defined for all values except what makes these denominators 0. Now, if I look at each of these two terms, we have different points that make one or the other 0 in the denominator. In the first one, this expression will actually be 0 when x and y are both 0. So this function phi does not exist at the point 0, 0. Likewise, this equation will be 0 when x is equal to 1 and y is equal to 0. So phi will not exist at 0, 0 or 1, 0. Now, if you actually just took the equations in under the radicals, x squared plus y squared, and find out what makes them less than or equal to 0, they can never be negative since it's the sum of two squared terms, and it can only be 0 at 0, 0. Likewise, x minus 1 squared plus y squared is less than or equal to 0 when it's actually equal to 0 because it's never negative since it's the sum of two squares. But it will be 0 when x is 1 and y is 0. So this function will not exist, not have a finite value at 0, 0 or 1, 0. So those charges are infinite at those 2 points. So now, if you were to graph these, notice that as the denominator gets larger and larger, so now these denominator values will be 0 at the point 0, 0, or 1, 0, but the further away you get from those points, the larger the denominator will be. And in that case, 2 over that, as the denominator is getting larger and larger, will actually be getting closer and closer to 0. And that's true for both of these two terms. So the further away you get from the point 0, 0, and 1, 0, the smaller this term becomes and the other term becomes, and so the electric potential function is getting closer and closer to 0. So let's look at a graph of this potential function. This is the graph, and you can see at the point 1, 0 and the point 0, 0, the charge is actually infinite. It doesn't exist actually at that, but the closer you get to those points, the smaller the denominator would be, which would mean 2 over that really small number that's getting closer to 0 is getting to be infinite. So you can see the infinite charge at those two particular points. Now let's look at level curves. If you were taking planes and intersecting for specific values of z, you'll notice that you would have contour curves that would be just these circles or ellipses, whatever they are. But as you got closer to the xy plane, as that z value gets closer to 0, the circles are getting larger. Now notice that in the level curves, that's visualized by seeing the concentric circles. So when you see circles that are concentric, they have the same center, that's represented by, in the graph, by either a peak or a valley. So if you have some sort of a high point, like a mountain, or you have some sort of a depression, like a valley, and you would end up having these type of concentric circles in your level curve. And so you can, when you see these type of concentric circles in a level curve, know that you have either peaks or you have valleys. So it could have also been going downward like that. And that would generate the same view in a level curve. You can't tell the difference in the level curve. So notice as you got further and further out, though, got lower and lower for the z values, it won't necessarily have these two circles. It's just going to be a wider range that would be the intersection, that contour curve for smaller values of z, getting closer and closer to 0. Okay, so look for the concentric circles. That's real important in being able to identify those peaks and valleys in your graphs of the surface.